All right, let's get into some real climate science. So it turns out that when most people are asked to explain the mechanism of global warming, uh, they cannot. The vast majority cannot. And so I'd like you to pause for a second, just pause the video, and think about how you would explain it. Do you understand it? Just try to say what the cause is. Pause now. All right, I'm assuming you did it and not, ignored me. So the atmosphere of our planet, we have been accumulating it for billions of years. The particular composition of it now is roughly 3 to 1 of nitrogen to oxygen. And it receives a lot of energy from the sun. A good portion of it stays on Earth and bounces back. Ultimately, all of the energy from Earth comes from the sun, but a lot of it is absorbed by the surface, the atmosphere, or the ocean, and it sticks around for a long period of time. So the reflection is slow enough such that we have an average temperature that's pretty high up, right? The temperature of space is pretty close to absolute zero, which is negative 270 something degrees centigrade, which is very, very cold. Earth is nowhere near that cold. And we're nowhere near that cold because, partly because of our atmosphere, right? So we get quite a bit of solar radiation, and most of it gets absorbed and is not really re-released for a long time. And so some of it bounces off right away by the clouds, reflected by the clouds. Some of it is reflected by the surface, but most of it's absorbed. The atmosphere is a very, very, very thin boundary between the Earth's surface and outer space. If it was an apple, it would be, if the Earth was the size of an apple, it would roughly be about as thick as the skin of an apple. It's very, 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 very thin. Right? And I said before it was about a 3 to 1 ratio of nitrogen to oxygen. Specifically, right now, it's around 78% nitrogen, 21% oxygen, and then the rest is made up of water, argon, carbon dioxide, and lots of other trace elements. This has not always been the case. There's been times in Earth's history where we've had no oxygen. There's been times where we've had much more oxygen. In the time periods where we've had no oxygen, obviously humans did not live, did not exist on the surface. Our ancestors didn't anyway. And in the times where we've had much more oxygen, plants were bigger, insects were much bigger, variety of things occurred. So what's happening is that the energy comes from the sun in the form of light and radiation across the electromagnetic spectrum, largely in light and infrared and UV. And it gets absorbed by molecules of various stripes. So the surface of the planet can be made up of anything, including heavy metals, whatnot, silica, very heavy things. The atmosphere is largely made up of just O2 and N2, a little bit of carbon dioxide, a little bit of water, and a tiny, tiny bit of ozone and nitrous oxide and carbon monoxide. And then really, really, really tiny trace amounts of other molecules. The way molecules absorb energy is they absorb it in their bonds. Okay, so the temperature just is molecular motion, average molecular motion. And as the sun hits these molecules, it shakes up these bonds more and more. So they're moving, they're vibrating at a higher rate. Bigger molecules can absorb more energy. That's basically it. That's the secret of all of this. The bigger the molecule is, the more energy it can absorb. Okay, so oxygen and nitrogen can absorb relatively little energy compared to the bigger molecules. Carbon dioxide is bigger, water vapor is bigger, right? These are big molecules. And so the fact that the atmosphere is so thin and it's so heavily overrepresented by O2 and N2 means that the balance that we have now can be upset quite easily by heavier molecules. If you've ever been to a humid part of the country, or if you've ever experienced humidity, you know that this is true. You know that the same temperature is much hotter in areas that are very humid. And the reason it's much hotter is because the H2O absorbs more energy and it sticks around you longer. So if we had heavier elements, heavier molecules, you'd see the same thing. You know that this is true. You've seen, like if you put wood in the sun or metal in the sun, the metal gets hotter faster and stays hotter longer, right? This is nothing, none of this should be surprising. And this generalizes across most molecules, right? So the bigger the molecule, the hotter it gets. It so happens that we've been putting out lots and lots of molecules out into the sky ever since the Industrial Revolution. So the traditional greenhouse gases are just going to be things like carbon dioxide. That's probably what you've heard about. Water vapor is tricky because it doesn't stick around for that long, but it is one of the bigger causes. You know, humidity, right? You get when things are humid, it's hotter. Methane, this is what is sometimes satirically called by some people cow farts. Sticks around for about a dozen years and then decays. That is, it breaks down from CH4 to CO2. The hydrogen mixes with the oxygen in the atmosphere and makes water, which decays, which falls back to Earth or does something. And the carbon that's in the CH4 bounds up with the oxygen in the atmosphere and makes CO2. And you can run the same thing for all of these others. Ozone, despite the fact that it is good to have it in the ozone layer blocking UVB and UVC, also absorbs more energy because of the extra oxygen atom than oxygen or nitrogen, right? And then all of the chemicals that I talked about in the last video. So we arbitrarily set the global warming potential of carbon dioxide to 1. So it's a value over 100 years. And this is roughly how much hotter it will make a single carbon dioxide molecule will make the atmosphere. We just set it to 1 because we have to set it, we have to set the baseline somewhere. There's no other metric to use. There's no like meter stick to use. So we choose CO2 as the the baseline. And then we can compare, taking into account various features of the molecules, like how stable they are, how likely they are to decay into other molecules that are heavy and will hang around the atmosphere, all of these factors. We calculate them and compare them to carbon dioxide. So if carbon dioxide is 1, and it's a small percentage of the atmosphere, but we set that to 1, then a single molecule of nitrous oxide, this laughing gas, is 300 times worse than carbon dioxide. Sulfur hexafluorine, 23,000 times worse because it sticks around for thousands of years and it's pretty big, right? And we can do that with all of the HFCs and HCFCs and that replaced the CFCs that were destroying our atmosphere. So you can see all of these are big molecules, and if the big molecules stick around in the atmosphere for very long, then they will make the planet warmer and warmer. We're adding blankets to the planet in the form of heavier gases. And we've known this is true for more than 100 years. So Svante Arrhenius calculated this in 1896. He was interested in figuring out whether Earth was going to go through an ice age again. So Earth had gone through an ice age in the past. We discovered this. And it was a big issue in the late 1800s to figure out if that was going to happen again. So he started doing the math, and he said, well, when you have carbon dioxide and you mix it with water, a portion of it forms something called carbonic acid, and it increased geometrically. And so if you get more carbon dioxide in the atmosphere, if you're producing more carbon dioxide, then it neatly increases arithmetically. And he did the math. He said, if from 1896, we doubled the amount of carbonic acid in the world by adding more carbon dioxide, which he knew that we were producing, the temperature increases about 10 degrees Fahrenheit, 4 degrees centigrade. If we cut it in half, then it goes down the opposite direction. So it's basically a thermometer for the planet, how much CO2 we're producing. He's not considering clouds as a factor, which is going to be relevant, not important, but well, important scientifically, but relevant historically. About 40 years later, scientists had been discussing this purely as a theoretical possibility. And so Guy Callendar does the analysis to figure out whether this so-called greenhouse effect has actually already occurred. And he calculated that since records started being kept, and these are very reliable temperature records kept by meteorologists all around the planet. We have more reliable records in certain regions going back way before 1880, but 1880, we have a pretty good global average of temperatures. And these are recorded by people without partisan affiliations, without agendas. This has just been recorded because it's relevant for transportation, for farming, for agriculture, for all sorts of reasons. You want to know what the temperature has been and what it will continue to be. So we want a reliable metrics, and we've been doing it very, 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 very reliably since around 1880. Guy Callendar calculates, based on what he's observed in the record, that the temperature has already increased by 1938 about a full degree Fahrenheit, and that carbon dioxide has increased about 10% in that time. He calculates that a good amount of this has been produced by human activities, and that there will be maybe a peak of about 2 degrees centigrade, about 5 Fahrenheit, which he thinks will stop there from being another ice age. Interestingly, 2 degrees is what the Paris Agreement, which we'll discuss in a later lesson, is hoping to keep the temperature limited to. Met with skepticism. In 1958, 2 decades later, Charles Keeling begins collecting data. So Arrhenius says that carbon dioxide will produce this molecule, carbonic acid, which will increase the temperature of the planet. Guy Callendar says it's already been happening. Charles Keeling says, well, actually, let's try to measure how good or how much carbon dioxide we're pumping out into the atmosphere. So I looked today when I'm recording this video that over the past 2 years, we've gone from around 405 or 406 parts per million to at the latest reading about 411 parts per million. When we get to the health section of this class, we'll see why some of this has been affected by COVID-19. The latest reading this afternoon is 411 parts per million. Not the highest ever recorded. That usually comes sometime in the summer, or at least the Northern Hemisphere summer. But you can see that over the past 2 years, it's gone up a little bit. If you look at the record since he started observing, we've been measuring more and more carbon dioxide every year or so. Since 1958, since we've been observing, people call this the heartbeat of the planet, right? And you can see the seasonal variation is pretty regular. It goes up and down with some regularity. So when he first started measuring, it was a little over 300 parts per million. We're now much higher than that. We're about 30-something% higher than that in terms of how much carbon dioxide is in the atmosphere. And when you look at ice core data from the beginning of human civilization, right? So that we weren't taking reliable measurements with thermometers, but we can go into the Arctic or the Antarctic, drill these cores, these big cylinders of ice, and make measurements under the assumption that the older ice is deeper in the ground or deeper in the core. We can calculate very precisely how much carbon dioxide was in the environment at that time that the ice was formed. And since civilization started, it's been pretty stable, somewhere between 255 and 270 parts per million. It has skyrocketed since roughly the 1800s. You can see it's called the hockey stick curve. And yes, it's true, if you measure in deeper time, before humans were around the planet, there were periods where the carbon dioxide varied wildly from a low somewhere in the 170 parts per million to a high somewhere close to 290 parts per million. So sort of doubling between ice ages. It still is at a speed that we've never seen, or at least that we've never detected on the record. And there's more carbon dioxide in the atmosphere now than we've ever seen in Earth's history. So a couple of years after this, after the data starts being poured through, scientists warned the president. They argued that by the year 2000, there would be about 25% more carbon dioxide in our atmosphere than the present. So this is Lyndon B. Johnson in the middle of Vietnam, civil rights legislation, and the space race. This is the time period we were spending quite a bit of time talking about. And so you can see why people were perhaps unconcerned by this, that we would modify the heat balance of the atmosphere to make marked changes in the climate that would not be controllable. See, 35 years seemed like far away, and 25% seemed like a bigger deal. People were worried about nuclear annihilation. But we knew about this in 1965. It took about 20 more years before the public was made aware of this. In 1988, Jim Hansen testified, this was a climate scientist, testified in front of Congress in public hearings that global warming has reached a level such that we can describe with high degree of confidence the cause and effect relationship between the greenhouse effect and observed warming. It is already happening now. He laid out several scenarios. He called one scenario A, one scenario B, one scenario C. This will become important in a class where we discuss climate denial. Scenario A did not map onto what occurred, and that's largely because the Soviet Union collapsed right after he testified. I mean, not immediately after, but shortly thereafter. This was a business as usual scenario, but one of the great economies of the country collapsed, and it led to a big decline in the amount of warming that the planet had seen. So anyway, scenario B is a little bit closer to what we have actually observed. And it actually maps on pretty closely to where we are right now. All right, so that's some history bringing us up to the early 90s. Let's present this argument. What is the point? What are people saying when they talk about climate change? In philosophy, we like to organize things very explicitly as what we call arguments. These are sets of sentences that are supposed to follow from each other, or assumptions that when combined lead to another claim. So premise one, we call them premises, these sentences. People emit gases, such as carbon dioxide, at a high rate. High here, don't read too far into that, just say, that's takes place over whatever amounts of gases that we produce. We emit gases such as CO2. Fundamental physics tells us that some of these gases absorb energy in the form of heat. So those are the images of all of the molecules vibrating and how they wobble while they vibrate when they absorb energy. And the reason I put multiple versions of the same one is because there's different motions that could happen. So, okay, physics tells us this. This is if you deny that they absorb energy in the form of heat, you're denying some basic thermodynamics, which we can have another discussion about if you want. The gases accumulate in the atmosphere. This was a premise that people did not accept for a very long time, right? So we thought that cars were cleaner than horses because there wasn't poop around, and that the output of cars was just going to dissipate in the atmosphere, and the atmosphere could never be changed by human activities. And then it got to the point where in big cities you couldn't see the stars anymore. And that's where we are now. We know they accumulate in the atmosphere because you can't see Vega from New York City. You can't see Sirius or Arcturus from Chicago. probably from Reno either. So, okay. Premise 4, these gases in the atmosphere behave in a way that fundamental physics says that they will. So unless the atmosphere changes how physics works, unless these behave differently because of things that we haven't paid attention to, despite decades of observation and study, then these gases will behave in the same way that premise 2 says that they behave. The conclusion from this, a tentative, well, it's not tentative, it's the first conclusion that we'll make from these three assumptions that are backed by scientific evidence, is that the gases will heat the atmosphere and the corresponding planets. The Earth will warm. So you can change premise 1 and say gases will be emitted and say that humans weren't involved, but we know that humans emit these gases. We'll talk about that later on. And we actually know that we emit more gases than other natural sources. An atmosphere's heating influences its climate. Okay, so that is a very basic assumption, right? So a hot atmosphere means that there's more energy around, and more energy means that there are more storms, that there is more droughts, that there is just more activity. If that's true, then the climate will change. So conclusion 1 is global warming, conclusion 2 is climate change. These are terms that are sometimes used interchangeably. They have both been used since the 50s. Just know that that's what we're talking about. Premise 6, life on Earth depends on the climate in a variety of ways. If that's true, then these changes will affect humans and other animals in a variety of ways. Assuming we depend on the climate being stable, the lack of stability will cause an effect, will affect us in some way. Premise 7, these changes will be much more costly to address in the future. We care about the future. If we care about the future, we should address climate change now. Therefore, we should address climate change now. Premise 8 is basically the one that everybody disagreed with, that all of your parents and grandparents disagreed with for a long time. They didn't care that much about the future. They didn't care that it was going to be more costly for this generation to address the changes of the past. Just like we don't care that it's going to be more costly to address in the future. And perhaps will have permanent consequences. Well, it has already had permanent consequences. Perhaps will have devastating permanent consequences. So this is the argument as cleanly as I can make it. Conclusion 1 is anthropogenic global warming. Anthropogenic means human caused. Premise or conclusion 2 is climate change. Anthropogenic climate change. Conclusion 3 is that this will affect our ecosystem. And conclusion 4 is a moral imperative that we should do something about it. If you want to deny climate change or deny that we should do anything about it, you have to pick one of these sentences and say why it's wrong. 1 through 9. People have chosen different sentences, right? So in the past, people have denied premise 3. People have denied premise 8. Some people have trouble with premise 5. I think premises 1 through 6 are pretty difficult to challenge in good faith. Actually, premise 7 as well, and premise 9. Premise 8, you just have to look into your heart to see if you agree with it. Okay. Has this happened before? Yeah, actually it has. The climate, the temperature has been hotter and the climate has been very different in the past. We've made observations on this based on inferences, especially before the Eocene. We have to make inferences based on like tree bark and these kinds of things, but we've inferred that the planet has been much hotter. It's been more oxygen. There were dinosaurs around. Humans could not live back then. I once tried to have an argument with somebody about whether humans could live around this time period, but nobody wants to, like, if people want to have that argument and not in bad faith, we can have that discussion. If it's just an attempt to distract, I don't know what the point is. Look into your heart. Why are you having this argument? Just to change your feeling of moral behavior or responsibility, perhaps. So yeah, the Earth has been hotter. Life has somehow survived. One thing that you'll notice, so the end Ordovician is this point. There's the end Permian, the KT boundary. Like there's these periods where you can see that the Earth has gotten much hotter or much colder very, very quickly. And one thing that you'll notice about this is that each of these is associated with a mass extinction. The 5 big mass extinctions, which again, like paleobiologists call them the 5 big mass extinctions, but depending on how you measure them, there's been between 2 and 17, just what you consider to be mass enough to be a mass extinction. The end Permian killed more than 90% of all family level diversity on the planet. So vast majority of everything that existed died. Not that far off from the KT dinosaur or explosion that killed the dinosaurs, that changed the planet, climate of the planet for tens of thousands of years. So we didn't see the sun for a long time. Volcanic activity just took over because there was a giant rock that whacked the planet, and it, yeah. So the Earth's temperature has changed a lot and drastically. And every time it's changed, it's led to a mass extinction. Because if your environment changes, you either adapt or you die. So surface temperature, I've already shown. The carbon dioxide increase. This is a corresponding temperature increase recently, zoomed into the previous chart. People have attempted to do climate visualizations. These are ways of representing how the climate has changed either worldwide or in your local region over the past 100 plus years. So we set this to the 20th century average, roughly between 1900 and the year 2000. We say, okay, let's average this out. Something that is bluer is going to be cooler than that average. Something that is redder is going to be hotter than that average. I've also organized my syllabus that way so you can see the years get hotter. On the bottom, you see the global average steadily increasing. Nevada's had a bit more fluctuation, but it again is also steadily increasing. So you can see that the temperature has changed quite a bit. There's other ways of representing that phenomenon. You can see temperatures over time every month and color code the changes or the decades. And you can see that we're getting closer and closer to this 1.5 and 2 degrees centigrade threshold, that are these thresholds that the international intelligence, military, and government agencies have all agreed is too hot to for life on this planet as we know it to continue. So we'll see massive die-offs. Well, we have seen massive die-offs. So something like 70% of described insects have died in the past 5 decades. Same with mammals. Arctic sea ice has decreased little by little to the point where this is going to stop in 2017. But the sea ice volume has decreased quite a bit. We can show actual pictures of this. We have images of those. And these greenhouse gases have increased precipitously. We started measuring some of these later than others. But we've seen greenhouse gases increase, and we can compare them to ancient history, right? So before humans were around, there was some methane, but not as much. We've tripled or quadrupled it in the past 100 to 200 years. Same with nitrous oxide. We've increased about 50%. Actually, it's probably about 40% of the nitrogen oxide in the nitrous oxide in the atmosphere. What's causing this? Well, lots of things, right? 3 major industries cause most of this: energy, transport, forestry, industry, agriculture are big ones. But energy, industry, and forestry cause the majority of this. There's about 100 companies that are responsible for 71 or 72, I forget, percent of the carbon emissions, greenhouse gas emissions. Which countries are causing this? China is the leader with 1 billion people. The United States, punching way above its weight, is right behind them. If we look historically, we've produced more than every other country, although China might overtake us pretty soon. All right, so here's a question. Is it natural? I'm gonna show a visualization that I really enjoy, that I think you might like, might make this clear. So what's really warming the world? Bloomberg Businessweek reports the observed temperatures from when we started keeping good records. And then they layer on top the orbit of the planet. And then they layer on top the sunspot, sun activities. We can layer volcanic activity. And then we can see whether all of them together, these non-human caused activities, in any way explain the observed behavior. If they did, we wouldn't have left these predictions, say in 1976, and not looked back. 1976, by the way, is the last year that was cooler than the 20th century average. We haven't had a cooler year since. Every year I make a bet that this year will be among the 5 hottest years on record. And if I'd been making that bet since I was born, I would have lost that bet 5 times. So, all right, let's go to human causes. Is it land use? It's not, it doesn't look like it. Is it ozone production? It doesn't quite look like it. Is it aerosols? Aerosols actually cool the planet, so you would expect aerosols to bring the temperature down, not aerosols. If you look at greenhouse gases, on the other hand, they map on pretty well, or at least better than the others, to the observed behavior. And if you compare them all, add them all together, all of the human factors together explain the observed warming better than all of the natural factors do. If you combine all of the factors, it's fucking spot on. So, is it natural? No. No, we're pretty confident. You look at the sunspots and volcanic activity, Earth's orbit, you look at all of the factors that it could be, none of them explain what's going on. Not even close. A volcano emits a lot of carbon dioxide, a lot of sulfuric aerosols, but it is not enough to explain what we're seeing. Scientists agree. The vast majority of scientific articles agree on this. And keep in mind that the way you get famous in science is to be right about something that everybody else is wrong about. Scientists seek out disagreement. They like correcting other scientists. Depending on how you measure agreement, it's well into the A range when you ask scientists whether they agree. So the evidence is pretty clear. The argument is straightforward. The scientists all agree. Humans cause the vast majority of the observed climate change and the observed warming on this planet. So I'm going to leave that there, and we can have a longer discussion about that in class. But before I do, I want to mention that I am hosting an event this upcoming Thursday at 5:30 p.m. on confronting legacies of health disparities. This is an event that I helped start and organize, and it should be pretty fun. See you there and see you in class.